Hi everyone, welcome to our talk today on scaling box search. Before I start, I'd like to share an interesting article. I came across this very interesting article a couple of weeks back on human perception of real time. So interestingly, I think you guys already saw what I was going to share. It takes 13 milliseconds for the human mind to register a visual stimuli. More importantly, if anything happens under 100 milliseconds, it's perceived as instantaneous. And that is why generally video games will have a response time within 50 milliseconds. Now guess what? If you have a search result that comes back to you at more than 1 second latency, the user completely disengages. He's not going to come back to your search page because it takes too long for him to find the relevant content. Now, we have come far away from like the 10 blue links problem where search was just find the results and display it. We want to do personalization, we want to do collaborative filtering, we want to do relevance on top of this, and all of this needs to be done within that 100 millisecond time frame, which I would like to think of as the holy grail of search infrastructure. Hi, I'm Shubhro. This is Anthony. We both work at Box. We work on the search infrastructure team. And today we are here to talk to you about how we use Solr, how we have scaled Solr, how we use Solr at a scale of like billions of documents and hundreds of millions of users. And what are the problems that happens when we do that? We will then talk about the existing infrastructure and then the new infrastructure based on Keyrings partitioning and how that helps us alleviate some of these problems that happen at scale. We will talk about shard growth and shard allocation in the context of Keyrings partitioning, and then some future work on the relevant side of things, because after all, we are in AI and search conference. So we have to talk a little bit about the relevant side as well. So without much ado, let's jump into the meat of the presentation. So for those of you who haven't used Box or aren't aware of what Box exactly is, it is a collaboration and content management platform that enables users across hundreds and thousands of enterprises to collaborate and securely share content with external customers as well as internal employees. It empowers them to collaborate in such a way that is non-intrusive and does not hinder productivity in the name of security. But as we know, at the center of every content management platform is content discovery. After all, we all want to find relevant content on the platform where we have all this data. And that's where Box Search comes in. Box Search addresses a few interesting use cases. There is quick search, as you can see on the top right. It's a type ahead style search, which quickly gives you file names that match what you are typing. It also has full content search, which includes snippeting and highlighting typical features that come out of Solr. We also have a lot of metadata with files. Now, this metadata could be dates of files, authors of files, who it is collaborated with, and some advanced metadata such as objects in an image that are identified through OCR or video transcripts. And all of this is searchable through Box Search. And then finally, we expose an API which enables external customers to build applications on top of Box Search to address unique enterprise use cases that they want to address. To do this, we need to index hundreds of billions of files. Our current index size as of yesterday is more than 600 terabytes. Guess what? This index grows at a staggering pace of like hundreds of millions of documents per day. Which puts our index growth at almost 2 terabytes a month. Do you want to venture a guess what it will be our index size? Well, I showed it already. But yeah, in 5 years, our index size will be close to a petabyte. And this is assuming the current growth rate. There's without assuming any acceleration of growth. And this is what actually motivated us to take a look at our existing infrastructure and make sure that it scales to the level of a petabyte scale index and still guarantees the kind of latency that we just looked at on the first slide, somewhere in that 100 millisecond boundary. So before we go into the new infrastructure, let's look at how the existing infrastructure looks like. So as you might have already guessed, like the core of it is Solr. We have a multi-cluster approach where we have multiple clusters across different data centers for DR and HA reasons. And these clusters are basically collection of shards which are hosted on physical machines. Unfortunately, we cannot run this on any public cloud system for security reasons and compliance reasons that our external customers want to adhere to. Whenever a user interacts with the web app or any API in Box, it generates an event. Now, the event could be generated because of uploads, because of edits of documents. Any of those events then get queued into a pub subsystem. We run a service called Search Worker on Kubernetes, which looks at this pub sub queue and gets the representation of a document from the representation service. Now, this will extract text representation of PDFs, documents, images, video transcripts, any text that you can extract out of the document that the user uploaded. Once this is done, the search worker then goes and indexes the file to all serving clusters to the particular shard it would route to. The way it does this currently is it uses the file ID to do mod-based routing. And we'll come back to this point and talk about the challenges that this poses. We also have an offline index in HBase, which actually stores the Solr document format after the extraction of the text, which can then be used by offline jobs that we run to reindex a shard or to rebuild a cluster. As you know, in Solr, you need to rebuild every time there's a change to the schema. And then for failures also, we need to reindex sometimes. The query pipeline looks something like this. Whenever there's a query on the web app side, the query is serviced by a service called Cerebro, which is again run on Kubernetes. The service has a federator which selects a particular cluster in a particular data center for that user and then fans out the query to every single shard in that cluster. Now, you might remember I mentioned in the previous slide that we are doing routing on the index side based on file ID. Unfortunately, at query time, we do not know the file ID of a search query because we do not know which files will match. So because we don't know the file ID, we don't know which shard to go to. So guess what? We have to fan out to every single shard. And we'll come back to this and see what are the problems with that. The other thing that we have is the permissions model. So the service also talks to application database, which has the permissions of the particular user who's performing the query and puts that as a filter query within Solr, as some of you may be aware of. The Cerebro service also had a rate limiter. This is typical of any service that that serves live traffic. You need to protect yourself against surges of traffic that happen from a particular user or enterprise. It also has a circuit breaker. The circuit breaker is the reverse of the rate limiter. We want to protect ourselves against shards that have very high latencies so that we are not querying shards that are in a wonky state. And that is what the circuit breaker does. And finally, we have a re-ranker, which waits for the results from all the shards that are there in the cluster. It re-ranks them based on external leads that we have, such as what files the user recently accessed, who the user collaborates with, and then we return these re-ranked results back to the web app. Now, another important aspect of any live distributed system is cluster management. The thing about any distributed system that we run on the cloud these days is failure. Nodes can go down because of disk issues or because of memory issues, and we need to be agnostic to these failures. We need to gracefully recover from them, and we need to still be available. I remember the whole 4 nines thing. So to do that, we run a service called Shard Health Monitor, which pings the Solr shards from time to time. If a Solr shard fails to respond to a ping repeatedly, it's marked bad in Zookeeper. Zookeeper then helps us propagate this information to all other services that interact with the system. And these services then know how to handle a bad shard. So for example, Cerebro will stop querying a bad shard. Search Worker will stop indexing to a bad shard. And then it does the other way around, which is when a shard recovers, it automatically puts it back into live indexing and serving live query traffic. So now that we know a little about the existing infrastructure, let's look at some of the problems. The first one alludes to the earlier point where I said that we need to fan out the query to every single shard. Guess what? That's a typical problem where you're bottlenecked by the slowest running shard. As you can see in this graph on the left below, when there is a spike in latency on a couple of shards, every single query experiences a latency spike. And this is horrible for user experience. Again, going back to the whole 100 millisecond thing, if your query took a little bit more time, the user is completely disengaged from your search system. The other problem that we have is with the throughput. If a single user or a single enterprise is executing expensive queries or high throughput queries, even before the rate limiter can kick in, this can get your shard into a wonky state because you're fanning out the query to every single shard. So every single shard experiences increased load. And finally, we need to grow organically. As we saw that our index is growing at a staggering rate, because of which we need to add more machines to a cluster. Whenever we add a machine, guess what? The shards grow, and hence the query fan-out grows. And we just make a bad problem worse. So what do we do about this? We definitely realize that by this point that the solution is to reduce our query fan-out. But the question is, how do we do that? One possible way is to cluster documents based on some particular information that we have available at the time of query. Now, obviously, we don't have this information available at, we don't have the file ID available at query time. But is there another possible information that we could use for this purpose? Enterprise ID seems to be a pretty good one. Because at the query time, you know the user ID of the query. And then from the user ID, you can figure out what is the enterprise ID. The other thing is within Box or in any enterprise case, users have access to only a subset of documents. And typically, this is within the number of enterprise, within the enterprise or within the collaborating enterprises. And as a result, we can shard the documents by enterprise and then fan out the query only to the querying user's enterprise ID and collaborating enterprise ID. And this, as we have seen, reduces the query fan out significantly, almost to one shard in most cases. The other benefit that we get from indexing from this sharding scheme based on enterprise ID is better index compression. And this happens because typically documents within an enterprise will be around the same content. So imagine a legal enterprise. They will have similar bag of words, which leads to better posting list compression in Solr and hence a smaller index footprint. Now, we never had this before because we were spreading documents from all enterprises across all shards. And finally, at the query side, you get better utilization of cache, such as the filter cache. If all the queries of the same enterprise go to the same shard, then you will possibly get better better hits on the filter cache and hence better latency, which is the final aim. But now that we know that we can do enterprise-based sharding, how do we actually implement this? One possible solution is through the Composite Id Routing. So Solr exposes a way for you to specify a shard ID based on, say, hash of enterprise ID. And this tells Solr how to route a document to a particular shard. This is pretty great, but unfortunately, you can't just use this out of the box because then even a large enterprise will just go to a single shard, which could simply blow up that shard. Guess what? There's another solution to this from Solr. You could use a variable number of bits from the sharding key to spread the enterprise across multiple shards. But unfortunately, reality is a little far from theory. When we actually did this, we saw that the distribution of documents across shards was still pretty skewed up. So why does this happen? The main reason that this happens is because typically you will have a few large enterprises which have billions of documents and a long tail of mid-sized enterprises with small documents. And when you apply composite ID routing, even with variable number of bits, you will get this kind of a distribution where few shards will get a large number of documents. So the other problem with composite ID routing is also that it's very predictive. You need to know the size of an enterprise before you know how many bits to use from the sharding key. So you need to maintain some kind of mapping of the number of bits to enterprise or some kind of threshold. Now, it's always better, as my friend here says, it's always better to be dynamic than to be predictive. And that's what brings us to Keyrings partitioning. Now, Keyrings partitioning is quite popular. It's used in key value stores that you might have heard of, mainly HBase, MongoDB. All of them use key-range partitioning for key value stores. In our case, we tried to apply the same concept to inverted indexes, and it worked pretty well for us, and that's why we would like to share it with you. Before we go into the details of how it is implemented, let's look at a conceptual state, what is key-range partitioning. So you pick a unique sharding key per document, and then you sort these sharding keys in byte order. What this gives you is a key range. Now, if you partition this key range into equal-sized buckets, where each bucket has the same number of keys, you will get logical shards which have the same number of keys, which is n by k. And that is what we started off to achieve. We wanted to get shards which have equal number of documents. The sharding key that we use for our case has the hash of enterprise ID in the higher order bytes. What happens is when we sort the keys based on this sharding key, all the documents of a given enterprise are clustered together, and that enables us to do an enterprise-based sharding. The good news is that if an enterprise has a large number of documents, partitioning the key range will automatically take care of large enterprises where they spill over to the next shard and the next shard and not overwhelm a single shard. We also use a folder ID, a hash of folder ID in the sharding key, and it enables us to index documents in sorted order of the folder. Now, what this enables us to do is to index documents within a folder with similar or very close sharding keys, and that gives us better dgap compression. Dgap compression is basically a posting list compression that comes out of giving close document IDs to shards, to documents which are similar. And the hypothesis here is that all documents within a folder have similar content. And then finally, we have the file ID for uniqueness. So now that we understand key range partitioning and how it works, let's look at how you would route a shard. So given that we partitioned the key range into buckets, we have what we call shard boundaries, which is the max key for each bucket or each logical shard. Once you have these, at index time, you could simply construct the new sharding key for that document and perform binary search across the shard boundaries to figure out which bucket that the new sharding key would lie, and then go and index the document to that particular shard. The query side is slightly more complicated because, unfortunately, as we said, we don't have the file ID or the folder ID at query time. But guess what? We have the enterprise ID. So using the enterprise ID hash, we can construct the smallest possible sharding key for that enterprise and figure the first shard where that enterprise lies. But we can't stop there because the enterprise could have been large enough and spilled over to the next shards. So we perform linear probing for the next few shards and identify till the last shard till which the enterprise is spilled. And then we will need to fan out to all these shards. But in this way, we are able to reduce the fan out from all the shards in the cluster to only a few shards. And guess what? Like if the enterprise is small, then mostly it will be just one shard. The infrastructure that actually implements this at Box looks something like this. We have a library called Lumos, which encapsulates the whole shard routing mechanism. So other services don't need to be aware of how the key range partitioning is working. Any service that needs to interact with Solr now needs to go through Lumos. Lumos interacts with HBase, which actually stores the sharding keys and the shard boundaries. And I'll talk about why we choose HBase for this particular reason. And then we have Zookeeper, which we use for shard coordination as well as update propagation. Now, HBase is pretty well suited for the use case that we have, which is maintaining the sorted sharding keys. And that is because HBase by default stores keys of a table in sorted order. So when you scan a table, you will automatically get the keys in sorted order. And this is pretty helpful for us because we can keep writing new keys to the key range. And then when we run a MapReduce job on that, it helps us to generate the shard boundaries. And also, HBase is pretty intuitively hooked into MapReduce. And tomorrow, if you want, we could even use Spark to do this, which helps us do this really quickly at a massive throughput. So now let's look at shard routing and how it happens in the new infrastructure. So a search worker or Cerebro instance, as we saw earlier, comes up in Kubernetes. It initializes something called the Lumos controller. The Lumos controller talks to Zookeeper to figure out what are the serving clusters and what version of shard boundaries to use. It goes to HBase and gets the shard boundaries, and then it caches this in memory. Now, the reason why we can do this is, imagine you have 600 billion sharding keys, for example, and then you break it into 200 shards. What do you get? You get 200 sharding keys, which are the max keys or the shard boundaries. And these are like 20 bytes each, so this is like pretty small. You can easily cache this in memory. The other thing is that these are pretty static. They don't change unless we rebuild a cluster. So unless we rebuild, this information can be reused for every single query, and then we can save on the latency of talking to HBase for every single query. Now, once this information is cached, once an index request or a query request comes in, using the algorithm, the bin packing, the binary search and linear probing, we can find out which shard to go to, and then we just route to that particular shard. Unfortunately, Keyrings partitioning doesn't solve all problems. Well, it solves all problems that we had, but it causes new problems. We moved from a system which had uniform shard growth and uniform distribution of keys, and we moved to this new paradigm where we are clustering enterprises by the enterprise ID. So we now become exposed to nuances of that enterprise's mechanisms, their shard growth and things like that. So if you see in this particular slide, in the lower one, which shows the index traffic, some shards, like the green one, has significantly higher index traffic than the other ones. So if you look at the shard growth that we see in 2 weeks, some shards have grown significantly much more, while there are other shards that have barely grown at all. The problem that this causes is that the shards are actually hosted on hosts which have a fixed capacity. The max capacity of the machines that we run are currently 3 terabytes. So if a shard keeps growing and exceeds this capacity, then we have a problem. We need to add a new machine to the cluster to take the new load of the particular enterprise or shard. Guess what? That's not a good story to tell your capacity team, because they will be like, hey, you have these shards which have so much capacity left. Why don't you go and use that one? Well, we exactly do that. And if you have ever seen a champagne fountain, you can understand what we tried to do, which is shard spilling. So when your shard has exceeded a particular threshold or capacity, we simply spill the shard to the next shard that has the most available capacity. And in this way, we are able to take advantage of the available capacity within the cluster than trying to add a new machine. Also, this can be very easily automated, and hence we can do load balancing without downtiming any of the services, which is a great thing. Now I'll give it to Anthony to talk about another problem that happens with Keyrings partitioning.
Yes, so Shubhro talked about one side of this imbalance. So that you have a lot of shards that could get a lot more indexing than other shards. This all could happen on the query side as well. So what we're going to do here is how we're going to allocate these shards to a node. So you can think about, we have these small partitions, and we want to put them on a machine such that it just doesn't hit one machine all the queries for one day. This is a problem for us because we see some enterprises have gigantic QPS, let's say during like midday, while some enterprises, just like let's say they're in Japan, they have it on another time of day. We want to level this out so that we have the least amount of machine usage. So the very naive approach would just to be putting, based on the range, we just put it to any kind of machine. We don't even think about it. Wrong approach. This has a lot of problems. So how we fixed it, we did some kind of scheduling algorithm, more like a bin packing algorithm. So we're packing the least and best, least used and most used shards such that it balances over all machines so that we could have probably a nice even load of queries per second. And this looks pretty good, but there's many ways to do this. There's a naive way, greedy ways, and an incredibly thorough way, which is like NP hard, takes forever, especially if you have thousands of shards. We just took a very simple, greedy approach where we zip up the lowest with the highest and put them together. How did this work, you might ask? It worked pretty well. Variance went down. It's smooth. It's nice and easy. And if you're on call, trust me, you like that. So that was mostly the work that we are doing on the infra side. There's also some future work. Particularly, you might be asking, how are we going to help out Solr with this? We don't want to just hold this as a little gift to ourselves. We want to give it out. So there is a plan to probably put this as another mode. We have an implicit mode, which we're running now. What we'd like to do is move to Solr Cloud and then turn what our mode is Keyrings Partitioning into another mode, something close to like a Composite Id mode. We'd probably extend the dock router and reuse Solr Cloud's Zookeeper coordinator as well, just to not like gut everything. So on top of that, we also are doing a few other interesting things at Box, mostly on the relevance side. Most of the relevance work happens on a layer on top of Solr. And this is sort of, if you saw some previous pages, it was a search federator. Here we do a lot of query alterations, expansions, classifications, and a lot of routing to different types of collections, and most importantly, some ranking. So before that, ranking is a little difficult for us. We're not like a web search or I guess a big e-commerce website where everything's public. Our enterprises really pride themselves on having privacy with us, so we cannot crowdsource query document pairs. This is because a lot of people put, let's say, health records, and we have HIPAA, if anybody heard of HIPAA. We can't just tell people, hey, does this look like a good answer to your query? It's illegal. So what we have to do, we have to figure out a different way to do it, and this is a very large problem for us. The second problem is that the document set for all users is usually very different. Within an enterprise, they have quite a bit of overlap, but outside the enterprise, you won't see the same types of documents. So a query such as, let's say some kind of financial report, pretty much everybody will have a different result set. Does that mean that what they click on is different and wrong? No. So this query document kind of pairing could have thousands and thousands of good documents for one query. But there are some pros. We have a semi-closed system such that we have people on Box could upload, download, edit, comment, and do a whole bunch of other events. Usually if one of these events happened after a search click, we sort of could see this as a good event. Like this means like someone bought the item that was in an e-commerce site, or they found what they were looking for. So we've sort of made a basic relevance pyramid where we're also trying to extract the last type of good search click. And that is when someone just tries to find the information. They don't have to upload, download, edit the event. They just found what they're looking for. This is hard to extract because you don't know if it's an abandonment or if it's a good query click. So what we do is we train to get certain types of parameters such as dwell time. So we could get a whole bunch of query document pairs that were not just from events, but also from good clicks. And then we use that to train a slew of other features. Some you might know, like BM25, which is Solr's most used relevant type of similarity function. We have our own functions as well with classifications and query alterations, and also a very large system for relationships to other people that you might have or documents you might have. And we call this the Box Graph. This was released a couple months ago, and I'll go through it lightly, but if there's any questions, there's also a nice blog post was posted about half a year on Box blog. So how this works is that you have a lot of explicit interactions, and we're trying to mine these explicit interactions to get implicit interactions between people. These implicit would be you upload a document, you edit a document. But by doing this, we could implicitly tell. If two people talk to one document or edit one document, we know that they're connected somehow. Let's say they're both in finance or they're both in research. By doing this over and over again, we can make larger graphs, and we know that people are connected to other people. We could get that Joe and Bob are connected because they both know Sue. This is a very strong feature set that's not just for personalization, but now you can use a lot of these personalization type of features to spread atop of organization. So you get implicit organizations, let's say finance or research, and they all might be looking for this type of document. We find this is a pretty good feature for us, and we're going to definitely extend on it. And hopefully, you could build tons of cool graph stuff. So maybe on the next year, we'll show some little extra slides on this. So this is the end of our presentation. Thank you very much for listening. If there's any questions, feel free to ask.
Trying to get my head wrapped around the idea, like concept you explained, like when a enterprise like outgrows a shard, you let it spill into a different shard. What do you want to explain what that actually means? Like, do you mean?
You want me to do it?
Yeah, take it.
Do you mean at real time you decide that your indexers are going to start ingesting the documents from the enterprise to a different shard, or do you like?
Yes, it happens in real time. So if you remember, I showed you a slide about cluster management, which is a service that we run to monitor the shards. So while we ping these shards, we also collect, like if you ask Solr for, if you hit the metrics endpoint, you can get back the size of each shard. So from the size of the shards, you can compute like what threshold are they at. And we have a particular threshold, say 80% utilization. If you have more than 80% of disk utilization, you decide that this shard is no longer good. And guess what? Zookeeper is extremely helpful for maintaining this information. So just like we maintain bad shards, we maintain shards which have exceeded capacity. If you want, like I could go into more detail, but basically what we do is we say that, okay, this shard has reached capacity, but in the cluster, what is the smallest shard that is available? And then we get that shard, and then we update a mapping in Zookeeper that says, hey, if an index request is coming to this shard, then spill it to this particular shard. Or sometimes if the shard is growing at a much faster rate, we can even spill to 2 shards. So what we did is we just split its rate of growth across more than 1 shard. So then what happens is when this information is updated, we use Zookeeper watchers to trigger the services that are talking to these shards to bounce. And when they're rolling bounce, they come up and then read this new information and then start writing to the new shard. Or if it is a query service, then it starts querying both the shards, because the older shard has the old data and the new shard has the new data. And this is like typically done it's a typical hot shard, cold shard kind of thing. Like a lot of enterprises, I think even Anthony will agree with that, do something like this where you have a cold index which has the old data, and then you have new shards which is just getting the hot index. Mm-hmm. And it's quite similar to that.
Yeah, you could almost see it as a parallel to how Lucene does segments. It'll have a lot of one segment and then start spilling over to a new one. And eventually, there's going to be a max amount. And what we have to do, like shard spilling is not the total end. At one point, all the shards will fill up. And what do? We have to do a full reindex. And you can sort of see that as a big merge. So it's sort of the in-between steps.
And do you also, at reindex time, maybe try to merge together the documents that belong to a certain enterprise that may spread across?
So at reindex time, what we do is like if we had any spilling for the shard or particular cluster, we just new call that. We already have the key range, which is maintained in HBase. So whenever a document is indexed, it writes the new key into that key range. And then like the key range keeps growing. And then when we reindex, we recompute, we run the MapReduce job that recomputes the shard boundaries based on the state of the key range at that particular instant. So it automatically rebalances the shards from the earliest data.
But it's a large offline process.
Yeah. You had a question?
When you decide that you do have to do a full reindex, how long does it take?
So typical reasons for a full index, one would be the schema changed in Solr, which is a pretty common reason. The other one is the cluster has completely exhausted capacity. Like we are at 100% on, or like more than 80% on all of the shards. Those are some typical reasons why we have to reindex. We have to do some partial reindexes if a node goes down, like there's disk issues, or there's some kernel patch issues because of which a machine needs to be taken out. These are some typical reasons when we need to rebuild. And as far as the time is concerned, originally we started off I think it took like a week to reindex. I think we are down to like under 48 hours to reindex a whole cluster, which is like all documents across all the enterprises. But we try to do partial indexes as much as possible, unless like we have to rebuild the whole cluster literally.
Go ahead.
Look, Dad, there's a feature. So I was making sure I understand one aspect.
Mhm.
Here's you have one large Solr cloud collection.
Yes.
Venture. Okay.
Right now,
So, is there? Did you look at the so-called migration feature of Solr Cloud, which allows you to basically extract? It's for the multi-tenant case, where one of your tenants, which is enterprise for you, is so large that you basically allow your biggest customers. Do you allow them to then put them separate? So instead of having one Solr Cloud collection, you would have one soup for all your little guys.
Yep.
And then as your bigger guys, you can split them off. Did you consider it? Or?
Yeah, we did consider something close to that. There's also one case I want to tell that's a little different than a lot of people. We have a lot of cross-enterprise collaborations. So if someone from one enterprise talks to, let's say, a different company, there's also a ton of that. So a lot of these kind of ideas of just putting everybody into one collection will break because sometimes they have to cross many. And this also happens there. It's almost like what you said is very similar. This is in 7, I guess. Solr 7 as an option?
Yeah, my collection migration has been around for actually a long time, but
Oh,
it's very much like
okay.
a very advanced feature that most people, it's documented. It's been there.
It's good. Yeah, we'll definitely look at it.
How many enterprises can one person search at once? Is that
So we have a collection. Before you see a lot of this kind of querying, we hit an endpoint where we get all the enterprises that they've been shared upon. This can be quite large for some users. Let's say salespeople tend to have a huge kind of share, while people who are like engineers tend to only stick to their own enterprise. This could be huge. It could be hundreds even. But those are rare. It's a definitely kind of exponential scale where only few have it all.
So I'm just curious, how many times do you change your schema? Is this a rare event?
Very rare event. We try not to, I don't think we have changed our schema in like the last couple of years at least.
No.
We only need to, we only change our schema only if we really have to add like some new information. We try to reuse some of the existing fields that we have. And I don't think that's a very common event.
You guys have a procedure to do that. You said you need 48 hours, whatever you said. It's 48 days. So do you have like a procedure where you have your system, the old schema is still operating while you build out a new index and you switch over?
We have multiple clusters. So we could just turn off one cluster and then put another cluster in, and then allow that offline cluster to do whatever we want. So we have usually a couple clusters up and running, a cluster ready as a backup, and another cluster that we're playing around with, let's say with a new schema to test for.
So it's quite similar to like when we rolled out Keyrings Partitioning. So we have a new cluster which has the new partitioning scheme, and then we have all the other clusters on the old partitioning scheme. And there is a lot of evaluation that we do. We first put the cluster like as a shadow, and then compare the results, and then do load tests on that. And then once it's warmed up, it's ready to go, then we swap the cluster in. And that's how we typically roll out features.
Your question was about data consistency, right? How do you keep that in sync so to make sure that there is no difference in data that is?
Oh, across the clusters. So because there might be separate schemas, we don't guarantee consistency across clusters. But if we try to keep it on our side, that is, like, we could have a schema change, and it might just be slightly different results, but the actual end information is not the same. It's just how we query it might be a little different.
Was your question related to schema change, or in general, how do we maintain consistency across clusters?
Yeah, when you were backing up asynchronously, you said you have two environments. One would be always behind like commission. And is that not a problem?
Oh,
so
it's
what
a
we
little
generally
different.
you want to take it?
Yeah,
Okay,
yeah. So it all comes from the same pub sub queue. So everything's fed in parallel all the time to the same machine. So you'll get the exact same information. But sometimes there might be slight differences in schema or code base while we're rolling out a new change.
Yeah, it's a typical dual writes thing. So we fan out the writes to every single cluster that is serving. And if you have a non-serving cluster, then remember we have an offline index as well. So the offline index is always the latest source of truth. So whenever we are building a new cluster, we go off that. And before we do that, we start putting the live indexes on top of that. So it's always caught up once it's serving traffic.
Back there.
Consider adding a layer of time series management of the data, so you can mentioned that all the machines like this finishes, so you need to index the whole thing. So if you manage this in a time-based manner, then you can add new machines only for your time transfer.
I could answer that. So what time-based, like hot and cold kind of paradigm of machines works well for logging. For us, not so much, because we'll have to hit. People are usually querying the newer type of documents a lot more, and they're extracting that kind of information. So those machines tend to be a lot hotter. We want to spread that out. So we want to spread the hot around the cold such that we have a nice balance of everything. So we don't have that hot-cold kind of paradigm.
I missed something. The clusters are, each cluster has the complete cortex.
Yes.
Mm-hmm.
And do you load balance across the clusters?
Yes.
Yes.
How many do you have?
So we have multiple clusters. I don't know if I can share the exact number, but we have 3 data centers, and we have these clusters spread across different data centers. And then at the query time, when the user ID comes in, based on the user ID, so the user ID is sticky to a cluster, so that if we had to debug something about a particular query, we can go to that cluster. But based on the user ID, we select a particular cluster and then send the query to that cluster. And then if ever a cluster is in a bad state, we just change, take that off and then put in a new cluster. And this is all managed through like application conf and stuff like that.
So I think we'll have like time for 2 more questions, but we'll also be outside if anybody wants to ask us after these 2 questions.
Basically, they are replicas, right? So
Each cluster is a replica of
replicas
each other.
cluster.
Yeah.
Any more questions? Actually, maybe. Okay, thank you.
Cool.